Energy calibration is performed using an option on the spectrum processing dialog window. It's under the calibration property page, and the idea of energy calibrating an XPS spectrum is that you perform a shift, and the shift should be applied to all measurements that are made at the same time. That is to say, you've got a set of oxygen peaks here where you can see shifts are evident, and each one of these rows represents a different measurement. So if we look at the molybdenum, say, you can see that there's a similar sort of shift going on here. And what about the carbon? Yes, you've got again a similar shift here. So these shifts in the energy are consistent along these rows, and the idea of the calibration is to work out what that shift needs to be to align all of these peaks. And one question might be that why do you get shifts in XPS peaks? And there's an explanation that a charge builds up on the sample because when you irradiate the sample with X-rays, electrons are being extracted, and these are the basis for the spectra that we're measuring, and this represents a current. And if there's no way for the charge to be replenished by a ground source, say, where electrons move from ground to the sample because we have an insulating sample, then what happens is the surface charges up, and the result is a shift. As the positive charge builds up, electrons find it harder to escape from the sample, so you find this fluorine 1s peak shifts when you have no charge compensation as part of the measurement. And similarly, you can see there's a shift in this carbon 1s. And these two measurements here represent a measurement from PTFE with charge compensation on, and a second one with charge compensation off. So the solution is to return charge to the surface, and this is performed by a number of means. One way is to have a cloud of low energy electrons that can be guided down onto the sample, and the idea is to form a steady state on the sample surface. And in this case, we've got the illustration shows that the sample and the sample bar are isolated so that it's not grounded, so the only source for electrons coming back to the sample will be from the neutralization mechanism. So when you do this neutralization, you end up with a steady state, and for different measurements that steady state may be different. And here's an example of two of these measurements from the molybdenum trioxide nanorods, where the oxygen and the molybdenum, and you can see the carbon 1s and the valence band, have all been shifted, and that's because for each one of these measurements the charge state is different. But using the calibration option and shifting the oxygen 1s to a known value, and in this case it's been taken from Scanlon et al., and that is 530.31 eV. That's a little precise perhaps, but nevertheless, shifting on the basis of this known value, the oxygen 1s, both of these move to a new position. And when I say move, that's the original positions, as you can see, are slightly higher kinetic energies, lower binding energies, and after compensation these align, the molybdenum 3D align, the carbon 1s, and also the valence band. So these represent two valid XPS measurements. They just have a different charge state when the measurement was performed. So returning to the data, what we'll do is illustrate how to do a charge correction based on an oxygen 1s. So first of all, let's do this in a manual way, and if we overlay two spectra and bring up the spectrum processing calibration option, these spectra are displayed in the order in which they're selected in the right hand side. So the red one, let me just illustrate that this is the first one. You can see that number 9 was selected first. It's first in the list. Number 75 was selected second. So if I hold the control key down, because the O1S/9 was selected first, it is the active spectrum that is going to be acted on by the spectrum processing dialog window, and if I hold a control key down I can visualize a movement, and it will update the display showing me the measured and the true values taken from that movement based on the cursor, and that's given me an offset here, and so the offset that I've just calculated should apply to all of these in this row because these are all measured at the same time. So when I say apply to selection, I obtain a calibration for the oxygen where they overlap, and then if I do the same here and overlay the molybdenum peaks, you can see that I have to some degree align the molybdenum peaks. So that was a rough form of calibration. Now let me just return these and I will undo that calibration, and then I'll do it in a slightly more sophisticated way where I will create a set of regions, and they will be based on the oxygen 1s, and this time I'm going to use an option which calculates an approximation to the data, and it's the polynomial regression type. I'm going to give it a rather extreme polynomial of degree 31, and the idea is that I should be able to approximate the data. Let me just show this on an individual, that you can see there's an approximation to the data, and the residual, that is to say the difference between the approximation and the data itself, is really rather good, and it's giving me a better approximation to where this peak maximum exists in these data. So if I propagate that region to the other selected oxygen 1s, I end up with similarly defined peak maxima, and these have all been defined by the position of this PR background type. And if I overlay these, don't need to overlay them, it's the selection that's important. So having selected in the right hand side the set of oxygen 1s, and if I enter the value that I believe to be the correct binding energy for this molybdenum trioxide, I will shift the region because there are regions defined here, and I can calculate now an offset for each one of these and apply this offset to all the measurements in the rows corresponding to these oxygen 1s measurements. So I've got the peak positions that are going to be calculated from the regions, and I've got a true value that I've set up, and I can press the apply row first region, and that will calibrate the entire data set that's open in this VAMAS file. So when I look at a pair of molybdenum peaks, I get a calibration that has been calculated based on the oxygen 1s, and similarly the carbon and the valence band. And as I step up and down, in fact you can see quite nicely in the valence band how well these now align. So although it looked like you had shifted data, and one of the things that XPS is looking for is chemical shifts, these were not chemical shifts, these were sample dependent shifts that had to be removed before we could start considering the binding energies of data such as these molybdenum. So we might perform a similar sort of measurement of a molybdenum position using, let me just adjust the region. So I'm calculating again the peak position. I'll actually use position for the tag field. So I've entered the string position, and I'll propagate this to the other molybdenum peaks that are all selected here. So I've got all my molybdenum selected, and I want to propagate regions. So I perform that propagation, and because I've got a tag field of position, if I go to the custom report and I select the regions, so it's copied through the name region for molybdenum 3D, and because I had the tag field set up as position, when I say tag defined report, it gives me a measure of the position for that peak. And as you can see here, this is the kinetic energy for that molybdenum peak, and if I wanted to, I could work out the binding energy by using an expression rather than simply the value that was coming from the region based on position. I can use the photon energy for these aluminium X-rays, and so I've modified my formula, and again I can use the selected VAMAS blocks and calculate the binding energies. These are the values that are now corresponding to the molybdenum 3D 5/2 peak that have been calculated after shifting with respect to the oxygen 1s.